This is sample problem 16.15. What is the pH of a 0.040 molar ammonia solution at 25 degrees C? So this is a base problem. It's based on the idea of NH3, which is ammonia. So you have to look up the values of the equilibrium constants for a weak base in the table in the chapter. So look for Kb values, which are the base dissociation constants. And for ammonia, which is NH3, you'll find that the Kb value is 1.8 times 10 to the minus 5, okay? 1.8 times 10 to the minus 5. Happens to be the same value of Kb that acetic acid, a very common weak acid, has for its own Ka. That's an acid, so it's Ka. So now let's do this very standard weak base problem. Here's the typical question. Find the pH of a solution of a weak base given its initial concentration. It's an ice table again. So here's what we're going to do. We're going to write down the chemical formula for ammonia. Okay, it's aqueous, so it's in water. React it with the water, and we're going to treat the water as a Bronsted acid, and we're going to treat the ammonia as a Bronsted base. So remember, the acid donates the H+, the base accepts the H+. So that means the H+ is going in this direction, right? It's going from the water to ammonia. How do we know that's true? Because we look up in the table that ammonia has a Kb of 1.8 times 10 to the minus 5, which means it's a base. So that means the hydrogen gets donated to the NH3. So NH3, if you give it an H+, you get NH4+. And water, if you get rid of the H+, you have OH-. Okay? It's not that bad of an idea to think of the water molecule as being almost like an ionic compound. It has two parts, H plus OH minus. And so if you donate the H plus, you just have OH minus, right? So Bronsted theory is, Bronsted-Lowry theory is all about donating and transferring. It's really transferring an H plus from one to the other. Okay, we're given the initial concentration of ammonia, 0.04. Water's a liquid, not involved in the equilibrium expression. Ammonium, 0, right? Hydroxide, 0. This is before the ammonia dissolves, so there's 0. Do your Q calculation. Q would be the products over the reactants. 0 times 0 over 0.040, well, that's 0. Q is less than K. K is given here. So that means the reaction proceeds toward the right, away from the reactants. So minus X plus X plus X. At equilibrium, we just take the initial and we add to that the change, ICE, 0 plus X is X, 0 plus X is X. Okay? So Kb is products over reactants. So X times X divided by reactants, 0.040 minus X. And if this looks just like a weak acid problem, you're exactly right. It's just like a weak acid problem. The only difference is we're solving for the hydroxide concentration instead of the hydronium concentration. But we use a value of Kb for the base, and we use our initial concentrations and the changes. Just like weak acid problems, this X is going to be pretty small. So we're going to make the assumption that it's approximately equal to X squared over 0.040. And that would be equal to 1.8 times 10 to the minus 5. Okay, so that means we'll solve for X. Why do we want to solve for X? That gives us the hydroxide concentration. Hydroxide is the key. We're trying to find hydroxide. Why hydroxide? Because POH is the negative log of hydroxide. And therefore, pH is 14 minus POH. So it's pretty nice. You can find the pH of this that way. Okay, so solve for x. How do we do that? Well, x squared is 0.040 times 1.8 times 10 to the minus 5. So x is the square root of that. Plus or minus the square root, right? Okay. So let's figure that out. .040 times 1.8 times 10 to the minus 5. Very good. We're going to take the square root of that. And you get 8.49 times 10 to the minus 4. Okay, unit similarity. Okay, so let's find the POH then. POH is the negative log of x, right? Because x is equal to the hydroxide concentration. Okay, so we're going to take the negative log of that. Log times minus 1. 3.07. And just be careful, this is not the pH. Let's come back to that. 3.07. That's the POH. X is the hydroxide concentration. So pH is 14 minus that. Am I right there? That sounds about right, 10.93. Weak bases, when you dissolve them in water, tend to give you pH values that are above 7, but not as high as 13 or 14 like you could get with a strong base. So therefore, 10.93 is a reasonable answer there. It does, of course, depend on the initial concentration. So if the initial concentration had been higher, we would have more, X would be larger, the hydroxide concentration would be higher, and we would end up with a higher pH. But it also depends on the value of Kb. So if you took a Kb that was 1.8 times 10 to minus 10, you would end up with a pH value that's much, much lower, significantly lower, because it wouldn't be as strong of a base. Remember, this Kb or Ka is really telling you how much X you're going to get. So for a weak base, it's telling you how much hydroxide you're going to get. For a weak acid, it's telling you how much hydronium you're going to get. So there you go.